So we will start with ILD for simply supported beams. So draw a simply supported beam AB. Draw a simply supported beam AB. And what are we going to do is we are going to place a unit load. Unit load in this simply supported beam, and the distance of this unit load is x distance from A. It is at x distance from A, and you have a section over here C, which is at a distance of z from A, and the span is L. Okay. So again I'm repeating, we are having a influence line diagram. We are going to draw the influence line diagram for simply supported beam. As I have told you, what is influence line diagram is, it is the graphical representation of the responses of a beam when a unit load moves from one end to the other end, right? So the simply supported beam having a unit load which is at a distance x from A, and you have a section C which is at a distance z from A. Span of the beam is AB. So another important thing which you need to note in ILD is always you should have the section, okay, because the responses of the beam will change along the section. If the section is at z distance from B, again the diagram will change. So always you are plotting the influence line diagram at a particular section, okay, and you are determining the reactions. So first we will go for determining ILD for reaction at A. Clear? So you are going to determine what is the function for the reaction at A when a unit load moves from A to B. So what are we going to do to determine reaction at A? Generally what we do, sigma MB equal to 0, right? So while writing down sigma MB equal to 0, you will get RA equal to 1 into L minus X by L, and that is equal to L minus X by L. You should do this, okay? It's not enough that you just write this RA. You should substitute in sigma MB equal to 0 in this B. Clear? Now you got a function for RA, that is L minus X by L. That is the function of RA for the ILD of reaction at A when a unit load moves from A to B. Now what you need to know, when you're going to draw a diagram, you should know the starting and the beginning. How will you determine what's the starting? Put in this function x equal to 0. When x equal to 0, what you will get the value for RA, that is equal to 1. And at the same time, now you need to determine the end point, that is x equal to L, and you get RA equal to 0. Now that you have all the values, so that you can draw the diagram. So what is your RA value at A? It is maximum 1, and at B you have it as 0, closest line. Okay. So what is this? This is your influence line diagram for RA. Clear? Influence line diagram for RA. Next we go for drawing influence line diagram for RB. ILD for RB in the simply supported B. Now what are you supposed to do? You take moment of all the forces in the beam about A, right? In the same way, you are going to get the value for RB. The sign conventions for bending moment is the same as before, no change. That's why I'm not repeating over here. So RB value you will get as X by L. Again, I'm repeating, you should substitute for sigma M equal to 0 and not blindly write this RB equal to X by L. Okay. Now, this RA and RB we had just in terms of X, which shows that it is linear variation. That's why I have drawn the triangle in the first case. So next what you need to do is determine at X equal to 0. At X equal to 0, what will get the value for RB? It is equal to 0. And at X equal to L, what's the value for RB? It is equal to 1, right? Substitute in this function and you get the value. Now again, for that simply supported beam, you are going to draw the diagram for ILD for RB. This is your diagram for ILD for RB. It's a linear variation and you have the function value as x by L. Write down ILD for RB and the beam values. Next, what you're going to see is shear force, right? Next, we need to go for shear force at C. ILD for shear force at C. Now, just draw the beam. Then you have a section C. Then you have this distance Z, this distance X, and you have 1 kilonewton. Okay, this is your A and B. Now that what you need to do is just write. In this case, the most important thing which you need to note is, as it is shear force, you need to consider the case when X is less than Z and the case when X is greater than Z. That is just before the section and after the section, because this clearly depends on the section. Okay, so before the section and after the section. So X less than Z is in this region, AZ region, right? Now in the AZ region, what is your shear force value? What you'll have for shear force from AC? You have it as RA minus 1, right? That is equal to minus x by L. Again, it is linear variation. Now to draw the figure, what you should know, at x equal to 0, you have shear force equal to 0. Then at x equal to z, you have shear force equal to minus z by L. Here you are substituting up to z only, right, for L, because it is x less than z and in this region. Now in the same way you go for x greater than z. In that case, what is, if x greater than z, your 1 kilonewton will be beyond AC. So when 1 kilonewton is beyond AC, what you will get for value of shear force? Just RA. And what is your function for RA? L minus x by L, right? Again, linear variation. Now to substitute, you can determine at x equal to z, you have this equation only, that is L minus z by L. And at x equal to L, you have shear force equal to 0. Now with these functions and values, complete drawing the ILD for shear force, right? Now this is the figure what you get for ILD for shear force. That is correct at the section where you have the section. You have it as a positive value. And here you have a negative value. This is positive, this is negative. Here write down the function value. Here also write down the function value. Write it as ILD for shear force. Clear? Next, we go for ILD for bending moment at C. Okay. ILD for bending moment at C. That is the next figure. Again, in this case also you have two conditions, that is x less than z and you have x greater than z. Both cases you need to write down. And for x less than z, just note in the figure, you can understand that your moment at C will be equal to RB into L minus z, right? So you get the variation as x by L into L minus z. Next, substitute for here at x equal to 0, you get it as bending moment equal to 0. Then at x equal to z, you get bending moment as z into L minus z by L. Now in the same way, the other case, when x is greater than z, you can write it as moment at C is equal to RA into z. That is equal to L minus x by L into z. Next, at x equal to z, you have bending moment equal to z into L minus z by L. And when x equal to L, we have MC equal to 0. Now that you can plot the diagram. Okay. Now again I am repeating, that is this RB into L minus Z. You will be thinking how it came as RB into L minus Z. It's nothing but you just write what you will be right at the section for this case? It is RA into Z minus 1 into Z minus X. This is what you will be getting. Right? Now you, upon simplification, you will understand this is same as this one. Okay. Now seeing, suddenly you will think, why when it is less than Z, the figure will be like this. When X is less than Z means section is over here and 1 kilonewton over here. When you take moment, you have RA into Z, then you have 1 into Z minus X. That's what I have written over here. Upon simplification, you get it like this. That's all. Okay, you'll understand it. That is what I mean is you should write like this and simplify. Then you'll understand that you reach up to here. In the same way, over this region, when X is greater than Z, what you'll be having? Just RA into Z. Okay. Substitute that, we can go for drawing ILD for bending moment. So ILD for bending moment, you will have it as a triangle and maximum value will come up on the section. Okay, where you have the section, you have the maximum value, and the function of the maximum value is Z into L minus Z by L. Another important thing which you need to note is, for the bending moment diagram, you should understand that when the load is in this region, in the AC region, you have the equation as X by L into L minus Z, okay, for this region. And when you go for the CB region, you have it as Z by L into L minus X. Why I am explaining this is because this will be required in the case of problem. Just understand this, okay? In this region, you have it as X by L into L minus Z, and in this region, you have it as Z by L into L minus X. So, with this, the bending moment diagram value is also complete. Another important thing is this derivation with the values, that is, you have the value as RA equal to L minus X by L. All these terms you should by heart, all these equations, okay? Then only you can apply it in problem. Sure. So you should study all these. What is the reaction equation? What is the shear force equation? Bending moment equation. All those things you should clearly by heart. Then only you can apply it in the case of problems.